All right, let's dive right into this explainer and explore a groundbreaking new way to scale quantum computing using sound waves. Now, if you follow quantum info processing, you already know that encoding data into particles of light, photons, is basically one of our absolute best paths forward. But how do we actually manage all that light efficiently on a microscopic scale? Well, today we're looking at a fascinating new paper that introduces the FRODO paradigm. And no, it's not taking a ring to Mordor, but it is a brilliant method that quite literally uses the power of sound to control quantum light.
So, before we get into the weeds, we first have to ask ourselves this massive, fundamental question. We're talking about guiding hundreds of independent streams of quantum data through a single optical waveguide. It's an incredible engineering challenge. How on earth do you keep these streams separate? And more importantly, how do you force them to interact and do computations without the whole thing just devolving into total chaos?
Here's what we're covering today. First, the frequency encoding problem. Then we'll introduce the FRODO paradigm, look at how sound actually mixes light, check out the proof from computer simulations, and finally, wrap up with the future of quantum chips. Let's get to it.
Starting with Section 1, the frequency encoding problem. Because to really appreciate the fix, we gotta understand the massive roadblock engineers are hitting right now.
So, frequency bin encoding. The concept itself is absolutely brilliant because it packs incredible amounts of information into one wire while naturally keeping everything phase stable. The bins are really just different frequencies or colors of light. You can think of it exactly like a multi-lane fiber optic highway. Each frequency is a different lane, and your quantum data, the photons, well, they're the cars. But here's the catch. Look at that brutal drop in success probability. When you actually try to process this data, to make these photons interact, or essentially switch lanes using standard electro-optic phase modulation, it gets incredibly messy. Your success rate asymptotically plummets to 50%. Why? Well, it's because these standard beam splitters are fundamentally infinite dimensional. When you try to force a photon into the next lane over, the signal just leaks. It bleeds out into empty lanes completely outside of your computational space, causing a massive data traffic jam. And fixing that? It requires huge, ridiculously complex photonic circuits just to untangle the mess, which completely ruins the elegance of using frequencies in the first place. You end up needing these sprawling tabletop setups just to fix the mess you made by switching lanes.
Which brings us to Section 2, introducing the FRODO paradigm. Enter FRODO, which stands for Frequency-Transverse-Mode Operations. Instead of using complex electro-optics that leak data everywhere, researchers figured out a way to use an acousto-optic scattering process. Literally, they're introducing precisely controlled acoustic waves, sound, into the waveguide to mediate the interaction. It acts as the perfect controlled on-ramp and off-ramp system.
This is a total paradigm shift. It means we can build perfectly controlled 2x2 frequency beam splitters. We can safely move quantum info between our highway lanes without losing data, and without needing to break the light apart, demultiplex it bin by bin, and stitch it all back together. The whole operation happens right there on the highway.
All right, Section 3, how sound mixes light. Let's actually zoom in and look at the physical mechanism inside the wire to see how sound and light interact on this microscopic level.
So check out these two highway levels. The researchers realized they needed to give the photons distinct group velocities. They engineered it so the even frequency bins travel up top in this symmetric mode, while the odd bins take the anti-symmetric mode down below. By giving the light two distinct spatial shapes, they created a strict separation. Basically, your even bins are cruising on an elevated highway, and the odd bins are on the lower level. They occupy the exact same wire, but their different spatial shapes mean they travel at different speeds. And here is the full architecture. Because those two levels are moving at different speeds, a photon isn't just going to accidentally jump from the top deck to the bottom. It needs a very specific push. That push, that's our sound. It's Brillouin scattering. An acoustic wave, a phonon, acts as a highly targeted bridge, providing the exact frequency and wave vector needed to pop a photon from a specific even lane down to a specific odd lane.
If we follow a photon's journey, it's really just 3 elegant steps to successfully change lanes without causing a pileup. First, a tiny microring resonator filters the even and odd bins. Second, a multiplexer shapes them into those distinct upper and lower spatial modes we just talked about. And finally, the acoustic phonon field kicks in, acting as that perfectly tuned ramp to let the photons switch lanes without leaking into the rest of the system.
Moving on to Section 4,
Proof through computer simulations. Because you might be wondering, does this actually work outside of theory? Well, looking at the data, absolutely. The rigorous computer simulations verify that cascading these FRODOs works with ultra-high fidelity. We're talking success probabilities easily crossing the 99.99% threshold as you increase the interaction length. The researchers tested this by simulating complex, multi-dimensional quantum gates, like the discrete Fourier transform. If you give the sound and light enough physical space to interact, the operations become nearly flawless. The leakage drops to practically zero. And here is where it gets crazy. 100% bandwidth utilization. This is a staggering improvement. In older electro-optic systems, engineers literally had to leave empty lanes, guard bands, between active frequencies just to catch all that leakage we talked about earlier. But because the FRODO paradigm's acoustic phase mismatch is so incredibly fine-tuned, you don't need guard bands at all. Every single frequency bin can be used for computation. Just look at this beautiful, clean ladder structure. By tuning the system just right, multiple pairs of bends can be coupled at the exact same time. It creates this ultra-dense, perfectly organized flow of data. You're essentially running multiple identical quantum gates in parallel, side by side, totally synchronized by the acoustic wave. Finally, Section 5, the future of quantum chips. So why does all this highly technical physics actually matter to you and the future of computing? It all boils down to manufacturing and scale. The absolute biggest takeaway here is that we don't need exotic, impossible to manufacture materials for this. We can build these acoustic bridges using the exact same foundational chip technology we already rely on every day. You don't need rare, highly specialized piezoelectric crystals. This works beautifully in standard silicon and silicon nitride waveguides. That is a massive deal because it means we can leverage existing CMOS fabrication plants to actually build these quantum chips at scale. It completely replaces those sprawling, delicate tabletop setups. Before, programming a quantum frequency processor meant relying on complex, brute force computer optimization just to guess the right voltages. FRODO flips the script. Because it maps perfectly to known mathematical models, it gives us a clean, predictable, analytical recipe to build whatever quantum gate you need directly onto a compact microchip. As the researchers put it, by uniting sound and light, we're looking at a hyper-efficient future for quantum info processing. We are officially moving out of the era of leaky, inefficient frequency splitters and into an era of ultra-dense, low-power multiplexing. The pure elegance of the frequency domain is finally being matched by the elegance of the physical hardware controlling it. With these huge roadblocks finally out of the way, it's honestly thrilling to think about how fast this transformative tech might make its way into our everyday lives. If we can pack hundreds of quantum light paths and the microscopic sound waves that control them onto standard silicon chips, the leap from a laboratory curiosity to a scalable quantum computer might be way closer than we ever imagined. Which leaves us with one pretty wild question. Are we actually standing on the brink of desktop quantum computers powered by sound and light? Now that's definitely something to think about.